Welcome to this explainer. Today, we're unpacking a really crucial, yet honestly underappreciated safety mechanism in modern electric vehicles. We're looking deep into the high voltage core of hybrid dual motor power conversion systems, or PCS, specifically zeroing in on high voltage and vehicle safety faults. And the big one we are tackling today, pre-charge failure. Think of the pre-charge circuit as the absolute ultimate gatekeeper. It's the only thing standing between the battery and a totally catastrophic power surge. If you've ever wondered how EVs safely manage those massive amounts of energy the millisecond you press the start button without literally blowing a fuse or, melting the whole system down, you're right where you need to be. Let's get into it. We've got a really solid roadmap for you. We're going to track this severe ASIL D critical fault completely from its physical origins right through the entire engineering lifecycle. We'll start with number 1, root causes of failure, then move into number 2, SW/HW co-diagnostics architecture. From there, it's into the prevention and testing side with number 3, DFMEA for design prevention, number 4, PFMEA for process controls, and finally number 5, DVP&R for validation testing. So before we talk about failures, what is a pre-charge circuit anyway? Well, think about it. When you turn on an EV, you absolutely cannot just connect the high-voltage battery straight directly to the system's uncharged DC link capacitors. If you did that, a massive instant flood of energy, what we call an inrush current, would just rush in, completely destroying components and literally welding the main relays shut. So instead, we use a pre-charge circuit. You can kind of picture it like a really high-capacity sponge that carefully and slowly absorbs a massive flood of electromagnetic energy. By routing the initial power through a pre-charge resistor, the system allows the capacitors to charge up safely before finally closing the main relays. It basically ensures the system doesn't drown in its own power. But that brings up a really scary question. What happens when this critical defense mechanism fails during a high-voltage startup? Like, what if that sponge can't absorb the energy, or the flow is somehow blocked? The stakes here are astronomically high. If this pre-charge sequence fails to complete within a very strict time window, the vehicle's computer immediately flags it as a severe ASIL D fault. For context, that is the absolute highest classification of risk in automotive safety. We're talking about a failure that could lead to fire, total component destruction, or even the loss of vehicle control. So let's jump into section 1, root causes of failure. We really need to look at the physical, electrical, and thermodynamic reality of why these circuits actually break down. Basically, we're looking at 4 main failure dimensions happening under the hood. First up is thermal fusing. Imagine a driver just mashing the start button over and over again. The pre-charge resistor ends up absorbing repeated blasts of energy, creating immense joule heating that simply cannot dissipate fast enough, literally melting the internal wiring. Second is contactor welding. Sometimes the main relay is already physically stuck or welded shut from a previous high-current spark. So when the system tries to pre-charge, the energy violently bypasses the resistor entirely. Third, we have DC link short circuits. This is a brutal hardware breakdown, like a semiconductor failing or a motor winding shorting directly to the ground. The energy pours straight into that short, and the capacitor never actually charges. And finally, sensing AFE drift. This happens when moisture or extreme heat causes the sensors to misread the voltage. It essentially tricks the computer into thinking the pre-charge failed when it actually hasn't. Now, what I find incredibly fascinating here is the stark contrast between physical destruction and what I like to call software illusions. On one side of the coin, you have catastrophic physical hardware breakdowns, like a dead short in your silicon carbide MOSFETs or that welded contactor we just talked about. The system is physically broken. But on the other side, you have things like electrochemical migration. Imagine a degrading O-ring letting in just a tiny bit of moisture, causing a localized electrical leak. The capacitor itself might be perfectly charged to 95%, but that compromised sensor sends a false, low-voltage reading to the MCU. The software sees this illusion, completely panics, and shuts down the vehicle. Both are ASIL D failures, but their root causes are just worlds apart. Moving right along to section 2, SW/HW co-diagnostics architecture. How exactly do we detect these failures, whether they're real or just an illusion, before a car catches fire? Well, we need a lightning-fast brain. Let's break down the exact millisecond timeline the system uses to diagnose a problem. Step 1 is dynamic slope monitoring. The very moment pre-charge begins, the software calculates the trajectory of the voltage rise. If within the first 50 milliseconds, that voltage slope is totally flat, the system knows immediately there's a massive short circuit. It smartly halts the charge right there at 50 milliseconds, saving the resistor from burning up. Step 2 is the voltage delta check. The absolute maximum time allowed for precharge is 200 milliseconds. Right at that 200 millisecond mark, the system compares the battery voltage to the capacitor voltage. If the gap between them is greater than or equal to 20 volts, the precharge has officially failed, and the system instantly triggers an emergency safe state. But hey, what if the computer itself makes a mistake? Enter the doer-checker dual-core architecture. This is super cool. You essentially have two synchronized processors acting like two totally independent security guards. The primary core, the doer, manages the precharge and calculates the voltage. The secondary core, the checker, reads a completely separate voltage channel and double-checks the doer's math. If their results differ by more than 5 volts, the system assumes a software glitch, like a random single bit flip in the memory, has occurred. It forcefully shuts down the relay drives in under 100 microseconds. And all of this leads us to one absolutely vital number: 60 milliseconds. This is your fault-tolerant time interval, or FTTI. When a precharge failure is detected, the entire system has to react, isolate the fault, lock the inverter pulse width modulation, and physically open the relays in 60 milliseconds or less. On top of that, it initiates a thermal cooling lock. It mathematically calculates the resistor's heat and literally prevents the driver from trying to restart the car for 10 to 30 seconds until things cool down. That tiny 60 millisecond window, that is quite literally the difference between a safe shutdown and a catastrophic fire. So how do we stop this from happening in the first place? Let's dive into Section 3, DFMEA, which covers key design prevention controls. How do engineers structurally fortify the system to prevent these failures from the get-go? It really starts with aggressive over-engineering. There's a strict design mandate that dictates the precharge resistor's single pulse energy rating must be at least 3 times the limit of the thin film capacitor's energy storage. You don't just build this thing to survive one normal charge. You build it to absorb an absolute beating. Engineers achieve this by locking in aluminum-housed resistors that are physically pressed against the metal casing of the unit. This allows them to dump heat instantly straight to the environment. And there are specific component upgrades that come straight out of this DFMEA process. Alongside those aluminum-housed resistors, engineers mandate precision thin-film resistors for the voltage sampling circuits. These need a temperature coefficient of resistance, or TCR, of less than 25 parts per million per degree Celsius. In plain English, it just means that even when things get incredibly hot, the sensors won't drift and cause those software illusions we talked about earlier. Plus, a reverse freewheeling diode is added to the circuit. This acts like a one-way valve, totally blocking any high-frequency AC power generated by the motor from washing backward into the precharge circuit and tearing it apart. Okay, let's step out of the design lab and onto the factory floor for Section 4, PFMEA, focusing on key process control methods. Because, let's face it, even a flawless design is useless if it's put together poorly. Manufacturers have to be obsessive here. To prevent loose connections that create heat and resistance, factories use automated torque angle servo screwdrivers to bolt down the bus bars and relays. This ensures the physical contact resistance stays well below 5 milliohms. They even use optical recognition to ensure the bolts have a specific phosphate coating for the perfect grip. Next, every single unit undergoes 100% automated end-of-line high-voltage calibration. The testing machines inject 400 or 800 volts directly on the assembly line to dynamically calibrate the sensors, permanently locking out any unit that shows temperature drift. Just look at this tolerance standard, less than or equal to 5%. That highlights the intense precision required during the soldering of the circuit boards. Every single board goes through 100% 3D X-ray or acoustic non-destructive inspection. If the total void rate, meaning the microscopic air bubbles inside a solder joint, exceeds 5%, or if even a single void is larger than 1%, the system automatically ejects the board right off the line. This is absolutely crucial to prevent relay control failures caused by solder cracking under heavy vibrations when the car is actually on the road. Finally, we hit Section 5, DVP&R, or Production Validation Testing. This is the absolute crucible of the engineering life cycle, where the assembled systems are pushed to their physical breaking points before a consumer ever gets behind the wheel. To actually pass production validation, this system is tortured. It has to survive 1,000 extreme rapid-fire precharge cycles at 800 volts without the resistor variance exceeding even 0.5%.
It must endure 500 hours of violent three-axis shaking, vibrating up to 2,000 hertz, while simultaneously being shocked with temperatures swinging from -40 all the way to positive 125 degrees Celsius. And through all of that, the contact resistance can't rise by more than 1.2 milliohms. But perhaps the most brutal test, engineers use hardware and the loop rigs to deliberately force 800-volt short-circuit faults right into the system. The acceptance criteria is non-negotiable. The system must detect the fault, log the exact P078 code, and execute an absolute shutdown in less than that magic 60-millisecond window. Zero smoke, zero fire, zero secondary damage. Which leaves us with a pretty big question. To push these physical boundaries even further, engineers are heavily leveraging dynamic 3D thermal simulation networks. These virtual models calculate the exact heat accumulation in these precharged resistors down to the microsecond, perfectly tuning those software cooling locks long before a physical prototype is ever even built. As we rely on increasingly complex virtual thermal modeling to optimize these incredibly robust defenses, where exactly will the next boundary of EV and PCS safety be drawn? It is a fascinating space to watch for sure. Thank you so much for joining me on this explainer, and keep exploring the incredible engineering all around us.